Okay, so here's our assumptions. We're going to assume that h1 is equal to h2. Our velocity at 1 is greater than our velocity at 2. With that being said, our pressure at 1 is going to be less than our pressure at 2, where our pressure at 2 is open to the atmosphere and equal to 0. We assume a velocity loss of 10 feet per second, which equates to 3 meters per second. That gives us our velocity at 1 to be 40 meters per second, our velocity at 2 equal to 37 meters per second, and we're going to take the density of air at 20 degrees Celsius, which is equal to 1.20 kilograms per meter cubed. Using Bernoulli's equation from these assumptions, we're going to set our h is equal to 0, our pressure at 2 equal to 0, and solve for pressure at 1. Solving for pressure at 1, we see that we get negative 138.6 joules per meter cubed, which is less than our pressure at 2, which is equal to 0, which is what we wanted. So what we see is that the atmospheric air has higher pressure than the pressure that comes around the ball. There's a pocket here that's made from this high velocity air flowing around the ball. So that's how that works. Although our assumptions showed us that the pressure at 1 was going to be less than the pressure at 2, that kind of gave us some insight on what was going on, but this is not exactly the whole truth. What actually happens is the air flows and comes around the ball, and when it hits the air on the other side, it creates vortices. Inside of the vortices are low pressure pockets, and those low pressure pockets are what creates the low pressure zone on the top of the ball. Of course, the high velocity air that flows around the ball contributes to the low pressure zone that keeps the ball from coming outwards away from this center, this zone here. The actual reason for this is called the Coanda effect, which is the tendency of a moving fluid to stick to a curved surface, like air over a plane's wing. When a jet of air moves through a surrounding stationary atmosphere, it pulls some of the stationary air along with it. This produces a low pressure shell around the jet stream. When there's a curved surface underneath the jet stream, the atmospheric pressure zone between the stream and the surface begins to diminish, and the jet stream is pushed downwards by the atmospheric pressure above the stream. This happens all along the curve. So when the air hits the ball, the stream hugs the surface of the ball. When the ball reaches the very edge of the stream, there's a low pressure zone on one side of it and a high pressure zone on the other. So the high pressure zone would, just as for the jet stream, push the ball back into the jet stream. And this is what we see is actually happening.